All right, let's get started. So we are going to go over exam number 3. We can either talk about it at first, or we can go over and then talk about it. Again, I'm always looking for feedback or opportunities to improve. So I don't know if people want to do that now or after the end. Any thoughts? No thoughts? I would imagine today's exam is going to be, the class is going to be pretty lightly attended because more than half the class just got out of an exam with me. So I would suspect that there's not going to be a ton of attendance, but I totally get it. I understand, but let's go ahead and we'll start talking. So this problem was the first problem. It says, given an open loop given the following, find the open loop transfer function. We really emphasize that the open loop transfer function was G times H. I don't know specifically what G is, and I don't know what specifically H is, but I know that the open loop transfer function is the combination of those two. And in our pole zero map here, we know that we start at a pole and end at a zero, and we start at the finite poles and end at the finite zeros of the open loop transfer function. So we start at the poles, so we know that these are x's, these are poles. These are starting points for my open loop transfer function, -2, -3. And we end at our zeros, -4. And we know that the number of poles has to be the same as the number of zeros. So we know that we have to have 1 0 at s equals infinity. But we're not going to put that in our transfer function. We're just trying to say we start at a pole and end at a zero. So we see with our root locus, we start at these two poles and we haven't ended at a zero. So we have to vacate the real axis and go up to the j omega axis. Then we jump back on because we need to terminate at a zero. So we terminate at 1 0 over here and the other one, which is at s equals infinity. So all we need to do for our open loop transfer function, GH, is s minus our zeros over s minus our poles. S plus 4 over s plus 2 times s plus 3. And that was it for this question. Questions on number 1. Fair, not fair? No comments? Okay. Can you hear me? Can somebody just acknowledge so that I can hear them talking too? So we're not hearing anything.
Yeah, that was fair, Paul.
Okay. I just want to make sure. All right, the next problem actually required you to do no root locus. I said, find the S-plane region. I never said, find the root locus that lives in the S-plane region. I just said, find the S-plane region. So you needed to draw an S-plane and then identify the regions where that exists, okay? So the first thing is, if you remember, the angles that we had over here, this angle, theta, was equal to the inverse cosine of our damping coefficient. And we know that our damping coefficient, there's my equation, because I can never remember all the specifics, but my percent overshoot equation, which is equal to 100 e to the minus pi zeta over the square root of 1 minus zeta squared. So my percent overshoot, how much overshoot I have, is related to my value zeta, right? So if I want more overshoot, then I decrease my value of zeta. Less overshoot means I increase the amount of damping. So essentially, anything that is on this side of this angle is valid to meet the damping coefficient of less than, the damping coefficient, the percent overshoot of 25%. All right. So you could have shaded in a region, and let's just pick a color. Anything over here, and don't forget, right, we have to have complex conjugates. So it has to go both ways, right? It has to be on both sides. So anything in that region at least will meet the percent overshoot criteria. The other criteria is, if you remember, any, let me change the color back to black. Any real term, whether it has a complex number or not, has an e to the minus alpha t. It could be times a sign of something, or it could just be e to the minus alpha t, right? And if you remember, the decay of this, e to the minus alpha t, has to be equal to, whatever that final value is, it's going to decay away. So we can normalize it. We can put a multiplier here, which is that same multiplier. So we can divide those out. If we want our value to be 2%, e to the minus alpha t is going to be equal to 2%. That becomes the 2%, not 4, 2% settling time, right? I just put 2s, but remember that's 2% settling time. So if I solve minus alpha, and I'll just call this t settling instead of 2 t, is equal to the natural log of 0.02, because 2% is 0.02, right? And my settling time is going to be equal to the natural log of 0.02 minus divided by alpha, okay? And if you remember, this is approximately equal to 4 over our alpha or our lambda, doesn't matter. On this axis, this is that e to the minus alpha t term, right? That's the real term that lives on that axis. So if we want our settling time to be less than 10 seconds, then t settling, which has to be less than or equal to 10 seconds, has to be less than or equal to 4 times zeta. So our value of zeta has to be less than or equal to 4 divided by 10. Well, we know that the value of zeta has to be a negative number, right? It has to start off at negative, let's say -3. And what number is going to be less than -3? Anything that goes in this direction. So let's change my color, and anything over here where this value of time is 4 over lambda, right? So now you just solve for lambda. So any time where this value is greater than, or less than, I should say, than 0.4 is a valid point. So now what we can do is we can say where those points intersect is a criteria that covers us. So anywhere over here meets the design criteria. Didn't have to do a root locus. You just have to know where to look, because if your root locus travels in there, then I can pick points that are in there. So remember, we're looking at design characteristics. We need to be able to interpret this figure and say, where do I pick a point? I have this wonderful root locus, but how do I pick a point that meets that criteria? And if you remember, we talked about this, right? This is one of the things in the exam review. Somebody was asking questions, and I think I also put this in the exam review. I actually put this figure to show you how to calculate these values. So that all that stuff was specified here. Okay. So again, I wasn't expecting you to do the root locus. I was just asking you to show me the points. Zeta is got to be 0.404 or greater, which means my angle of theta is going to be less than that. And my settling time, the time has to be less than -0.4 seconds. or the alpha term has to be less than minus 0.47. And that was it. That's all you needed to do for this problem. Questions or comments on that problem? Okay. Was it a reasonable question to ask? Okay. I think if you, and we can bring up the exam review if you want, but in here, I think I included. Thought I included that figure. Maybe I didn't include it. I know we presented it at class. During class. So yeah, I guess I didn't include it in here. But I did say, identify regions and locations on the S-plane to meet design criteria. And we were talking about that. I brought up that figure. So that's problem B. Okay. Any discussion, questions on that? Yep. One more page, sorry. I have a finger dexterity. Any questions or comments on that one?
No, I'm set.
Okay. All right, let's go to number 3, which is you actually had to do, a root locus on number 3. So number 3, let's just go ahead. We have to do a root locus, which means we immediately go and do the the open loop transfer function. So some people did the closed loop transfer function, and remember, we stressed that the day before the exam. You have to use the open loop, not the closed loop transfer function, because we start at the open loop poles and we end at the closed loop, the open loop zeros. So my GH is going to be equal to 1 over S plus 7 times S plus 1 times S plus 2. We're going to specify the poles. So we have -7, -1, -2. And the zeros, we have no finite zeros, but we have 3 at S approaches or equals infinity, right? So now we have enough to at least start to draw the real axis root locus. So let's draw that over here. We have -1, -2, and -7. Now I'm going to start labeling, right? I'm going to start labeling where the poles and the zeros on the real axis from right to left. 1, 2, 3, and those are sequential. And then it lives between odd and even, right to left, but not between even and odd. And then between odd and even over here. Well, we can see we go from 3, but there's no 4. Well, actually, there's a 0 at S equals infinity. So we start at a pole and we end at a 0. This root locus terminates at that 0. These do not. So we know that we have to approach some S's and infinities, and we know we already have one. We solve for it. This is 180 degrees. So we have to solve for our asymptotic thetas. So our asymptotic thetas, let's see, it's going to be equal to, I don't have the equation. I don't know why I didn't put the equation up here, but I know I have, this is n minus m, and this is r times plus or minus 180, and r will never exceed m minus m. So this is going to be equal to, we'll start off with 1 times plus or minus 180 all over 3. that equals plus or minus 60 degrees. And then my next one is I'm going to go up to 3. 3 times plus or minus 180 because it skips divided by 3, which is equal to plus or minus 180, which is the same angle, right? So we got our plus or minus 180 right here. The plus or minus 60 is those are the two that we need. So now what we need to do is figure out our centroid, where those angles take off. So that's the sum of the poles minus the sum of the zeros. So, I mean, sum of the zeros minus the sum of the poles. So we have no zeros, so that's 0, minus the sum of the poles. So, or oops, backwards. It's the sum of the poles minus the zeros. Oh, come on, why isn't it auto erasing? So sum of the poles minus 1, minus 2, minus 7, minus the sum of the zeros, all over n minus m, which is 3. So I've got negative 10 over 3, or minus 3 and 1/3. So at 3 and 1/3, which is about over here, I draw asymptotes. And I know I'm going to approach those zeros that are at s equal infinity at 60 degrees. So I'm to the left of the j omega axis, which means I'm going to have some j omega crossings in here, correct? So the j omega crossings are when I do Routh-Hurwitz. But I got to do Routh-Hurwitz on the characteristic equation, right? So I need my characteristic equation, which is 1 plus k GH. And I'll just ignore k for the, no, I'll keep k in, sorry. I want to keep k in. So that's 1 plus k times 1 over, let's see if I can do this moderately quickly. So I have s plus s squared plus 3s plus 2 times s plus 7. That's when I just multiply out the s plus 1 times the s plus 2. Now, this is going to be equal to s cubed plus, let's see, so I've got 3s squared plus 7s squared, so that's 10s squared, plus 2s plus 21s, plus 14, if I did that correctly. So I'm just multiplying up the denominator, plus k, all over s plus 1, times s plus 2, times s plus 7. I don't care about the denominator, because this whole thing is being set to 0. So all I need is the numerator, which means I need to do the Routh-Hurwitz on this equation over here. So this is row S3, S2, S1, S to the 0, 1, 23, 10, 14 plus k, negative 1/10 times the determinant of 1, 23, 10, 14 plus k is going to be equal to negative 1/10 times 14 plus k minus 230. And then we know the next term is 0. So this whole row has to be equal to 0, right? So we know 14 plus k minus 230 has to equal 0. So k is going to be equal to, let's see, 230 minus 14. So 230 minus 14 is 216. Is that correct? So for my value of k equals to 216, then I get a row of zeros. Then I can go back to my auxiliary equation, which is equal to 10 plus 14, 10s squared plus 14 plus 216. And then set that equal to 0. So 10s squared plus 230 equals 0. So s is equal to the square root of negative 23. Or s equals plus or minus j square root of 23. And that's the j omega crossings here. Okay. Questions on that? Because the only other thing we need is when we look at our root locus plot, we have on the real axis two root loci that are approaching each other, so they have to break away. So we have to calculate the breakaway points. The breakaway points, we take the partial of -1 over GH with respect to S. We evaluate that at our S equals sigma. So this is sigma, then I wrote 0. And then we just use root solving for that. So take the partial of, and I'm just going to write this down, -1 all over 1 over S. What did I have? I have this right here, s cubed plus 10s squared plus 23s plus 14. S cubed plus 10s squared plus 23s plus 14. I believe that's correct. Let me just go back up and double check that. Yep. So I'm taking the partial of that with respect to s, which means I'm taking the partial, of negative s cubed plus 10s squared plus 23s plus 14 with respect to s. So that is 3s squared plus, what's going on? Sorry about that. 20s plus 23. Negative is up front here. Set that equal to 0. The negative term goes away. So you just have to do root solving for that. So let's plug that into MATLAB and solve for the roots of this equation. So roots of 3, 20, 23. And I have minus 5.19 and minus 1.47 or 48. So this is going to be equal to S plus 5.19 and S plus 1.48 equals 0. Out of the two roots, minus 5.19 and minus 1.48, what lives on the root locus? Which point of those two is the valid one? Remember, it has to leave the real axis at that point, so you have to have root loci. So looking at the real axis, where is the real locus? Is minus 1.48 a place with the real axis where you have a root loci? Yes. It's between minus 1.2 or minus 1 and minus 2. And the other point is someplace over here. There is no root loci that live there. So I leave minus 1.48. And that's how you would do this root locus problem. Oh, somebody have a chat? Yes, thank you, Joanna. Minus 1.48 is the location. Questions on that? Fair, not fair? Did you feel like you had enough practice?
I thought it was a pretty fair question.
What's that?
I thought it was a pretty fair question.
Okay, Jordan, what did you say? I'm sorry. Okay. This one was actually a really easy derivative, right? Because when you inverted it, there was no quotient rule. It was all in the numerator. And so you just did it that way. So I tried to make it even easier. Just say, you know what? I'm not going to expect them to do partials. I mean, it really wasn't a partial because it was all values of S. But you didn't even have to worry about the quotient rule. You could have just zipped it out and been done. Okay. The other cool thing about it is hopefully what you start to see is you can use, because you're learning about this process, you can actually start to see, oh, what do I need and what don't I need? Angles of arrival and departure, don't need it because I'm not arriving or departing complex routes or complex poles or complex zeros. I'm just leaving real ones. So it's much easier. And I arrive at complex zeros, but they're way out of infinity. So I don't care what those values are. But essentially, this is it. I debated if I was going to ask you to find a value of K for gain, but then if you would have gotten your root locus wrong, then it's very difficult to calculate a value of K, right? But I almost said calculate if -6 is a valid pole zero location, but I thought that was enough. TV land, you're awfully quiet. Any questions other than Tom? Fair, not fair?
Yeah, I thought that was fair. You went over it, but fair enough. So
Okay. Because in my opinion, this was the problem with the most amount of effort. Like you just had a lot of steps to do. This was the problem. On number 2, I wasn't sure if people were going to struggle. I know we went through that a lot in second order systems and we reviewed it a little bit in root locus. But again, that's the whole purpose of root locus is where can I pick a point that meets design criteria? So that's why I wanted to stress that. All right, well, let's do number 4. So number 4 is solve for ESS for a unit ramp. And I didn't ask you to do all the other ones because I said, if you know the system type, you're all set. So the first thing we're going to do is look at the open loop transfer function, which is K over S times JS plus B. We know that this is a type 1 system because the number of integrators in the system is 1. So a type 1 system has a unit step error of 0 and a unit parabolic input error of infinity. So we don't need to worry about those. We only have to calculate our velocity constant and then our ESS for a ramp. Our velocity constant is the limit as S approaches 0, S times GH, which is equal to the limit as S approaches 0, S times K over S times JS plus V. Cancel, cancel. Now I take the limit as S approaches 0, makes the J term go away. That becomes K over B. Right? Then our ESS for our ramp is equal to, if it was a unit ramp, you say 1 over K sub B. If it's not, you could put a constant there, whatever the value is. But some people got tripped up over what was K versus what was the input value, the multiplication. So if you're confused, call that A. But we'll call it just a unit ramp. So that becomes K over B equals B over K. Questions on that? Fair, not fair?
Yeah, no, that one was relatively straightforward.
Okay,
Yeah, that was a pretty fair question, in my opinion.
okay. The last one, again, because we're engineers, we got to do a lot of design. So on number 5, we had following loop gain. And if I don't tell you, it would be the open loop gain. So my GH is equal to K over S times S plus 2, S plus 3, S plus 1. Again, I told you it's a unit ramp, but you can still look at it and do the calculations because we know it's a type 1 system. So we're going to solve for our K sub V. Limit as S approaches 0, S times K over S, S plus 2, S plus 3, S plus 1. And this cancels out, and what I'm left with is K over 6, right? My steady state error for my ramp has to be less than or equal to 3. My ESS, which is 1 over KV, has to be less than or equal to 3. So 1 over K over 6 has to be less than or equal to 3. 6 over K has to be less than or equal to 3. K has to be, let's see, greater than or equal to 2. I technically said it has to be equal to 2, so that makes it even easier. But if you want to be less than 2, you have to have a value greater than or equal to 2. Sorry, you want a value of steady state error to be less than or equal to 3, then K has to be greater than or equal to 2. And that was it. Final thoughts on the test. Here's your chance to discuss. Overall, do you feel like you were prepared well enough? Homeworks, labs, presentation? It is still confusing?
Yeah, but I feel like we covered enough of process. I would say, like, yeah, that makes sense for like the problem.
Do you feel like you needed more discussion on it during class, or more examples to do, or more homework?
I think it's more examples, but I like
In class examples? Okay,
the process clear in my head, but it was a lot.
yeah, it's a lot of math. We actually went pretty slowly on the material. If you remember, I think, because we spent those first 2 classes, we went over how to do the rectangular and polar calculations. So I wanted to make sure everybody had the math concept understanding, at least from that perspective, because we're fairly relying on it. But after that, it hopefully was more straightforward algebra, but there's a lot of concepts that we're applying for sure. Generally, I think the average was an 83, so I think people seem to have gotten the concepts pretty well. So I was generally pleased with the results. Okay. How about you TV land folks? Any thoughts or discussions?
Overall, I thought this is a pretty straightforward test.
Okay. You feel like it was a reasonable enough assessment tool to see if your learning was what if you had learned the material well enough?
Yeah, I'd say so. It was a pretty good, I guess, way to check to see how much, like, what we need to cover more for the upcoming final.
Yeah, we only have really one more class, right? After this one. And then we do an end of year review, essentially. No, I don't think so, because we just have. We don't really have any new material, so. Okay,
Paul, are we having lab next week? Sorry to cut it.
yeah, that was a question. We probably will not, only because we don't really have. I mean, we might get a little bit of Bodie plot discussion on Tuesday. But not really enough to do anything with it. So we probably won't have lab.
Okay, I just didn't hear his question, so awesome.
Yeah, no,
Thank
that's
you.
okay. All right, well, since most of you had a test with me just a little while ago, I will let you out right now, unless there's any other questions.
Have a good one.
Have a great day, everyone. Take care.
Thank you. Have a good weekend.
You too. Thanks, Tom.